This video solves problem 11 of unit 12. In it, we have two metallic plates with a certain area of 4 square centimeters, which are separated by a distance of 2 centimeters. So this is A and this is D. And then they are both connected to a battery. We will see batteries in the next unit. This is the positive side, this is the negative side, in a way that if we put here point A and here point B, the difference, the potential loss across the plates is called V, and it's 120 volts. Okay, so they're asking us to find what is the magnitude of the electric field between the plates. We know that there is a relationship between the potential drop, the potential difference across the plates, and the electrical field, because this is a parallel plate capacitor, and it's just the electric field times the distance. So to know the electric field, we just have to divide the potential difference by the distance. And if you do this, this provides 6.6 times 10 to the 3 volts per meter. In B, they want us to calculate the surface density charge and the total charge of the plates. This is sigma and Q. Okay, so for sigma, we know that there is a relationship between the electric field between the plates and the surface density charge. If you don't remember, you can go back to the slides or back to the explanation, or you can also apply Gauss's law, remembering that there is no electric field outside of the plate, so there is only the electric field inside. So if you go back to the notes, you will see that the connection between the electric field and the surface density is just that the electric field is the surface charge density divided by epsilon sub 0, because we think that there is just vacuum between the plates. Okay, so this leaves you with an easy calculation, that is that the surface density charge is going to be the electric field times epsilon sub 0. If you do the numbers, this provides 5.31 times 10 to the minus 8 coulombs per square meter. To calculate the charge, we just have to remember that the total charge is going to be the surface charge density times the surface. Okay, so the surface was 4 square centimeters. Sorry, this should be a square. 4 square centimeters, and here we have the surface density charge. So if you do the maths, the charge is equal to 2.1 times 10 to the minus 11 coulomb. Then they are asking what is the total energy stored there. So to calculate the total energy stored, as we have the charge and we have the potential difference, this can be easily solved by applying, remembering that the energy stored in a parallel plate capacitor is 1/2 times the charge stored times the potential difference. So if you do the maths, you have the charge, you have the potential difference. This is 1.3 times 10 to the minus 9 joules. Okay, so in sections D and E, they're talking about an electron that is released from the rest at the negative plate. So it's released from point B, and it goes it goes to point A. And they're asking in D, they're asking what is the potential energy lost by the electron when it reaches the positive plate. This is point A, because this is the positive plate, this is the negative one, and the speed of the electron just before it collides with the positive plate in section E. So to do that, we just have to remember that the amount of energy is going to be equal to the charge times difference of potential, the potential difference. Oops, sorry. So this is going to be the charge of the particle, which is the electron, times V at the endpoint minus V at the initial point. So this is 120 volts, and this is the charge of the electron, which is 1602 times 10 to the minus 19 coulombs. Okay, so this negative charge we already knew, because we know that there is a loss. Okay, so it's decreasing the electric potential energy. So if you do the maths, this would be minus 1.9 times 10 to the minus 17 joules. You can also skip the minus if you want, because we know it's lost. Okay, and to solve section E, we just need to use the energetic constraints. We're going to think there's no friction in this problem, and that the electron is just transforming its initial potential energy into kinetic energy. So we would just say that the total electric energy in point B plus the total kinetic energy in point B has to be equal to the total electric potential in A plus the kinetic energy in A. We know that it's set from rest, so this is 0, so we just need to know that the kinetic energy is going to be the energy at B minus the energy at A. This is minus the loss. Okay, so we know that the kinetic energy is going to be 100 when it reaches A, it's going to be 1.9 times 10 to the minus 17 joules. So from here it's easy to calculate the speed, because we know this kinetic energy is 1/2 the mass of the electron times its speed, squared speed. So from here we can just derive that the speed is going to be 2 times the kinetic energy at point A divided by the mass of the electron. If you do the mass and you look for the mass of the electron, you can find that this is 6.5 times 10 to the 6 meters per second.